Hello, and thanks for watching this video. I'm Hamid from MIT. In this video, I'll be telling you about my research on self-reconfigurable microimplants for cross-tissue wireless and batteryless connectivity. This is a joint project with my colleagues Ray, Hun-Seok, Ananta, and Fadl. This talk is about how we can design tiny intelligent microchips, like the one in my hand, and implant them inside the human body for medical sensing applications. Last year, a man received a microimplant under his skin live at the World Mobile Conference. But the microimplant is very limited. It could be only implanted at superficial depth, and the only thing you can use it for is to identify the person. In fact, in a recent op-ed article in Popular Science, someone who received a microimplant wrote, "My implant is both less scary and less useful than you might think." Now, while implants right under the skin are not very useful, if you can take them and put them deep inside the human body, they have enormous applications in digital medicine. So 2 years ago, we set out to build microchips like this one, which has no batteries, and put it deep inside the human body, and we wanted to communicate with them from outside the body. So how can we power up and communicate with these microchips when they have no batteries? Our approach is to wirelessly power the microimplant. A device outside the body shines a wireless signal, and the signal goes through the body. When the signal reaches the sensor, it will harvest energy, power up, and communicate with the device outside. This would enable many applications in digital medicine. A major application is in ultra-long-lasting drug delivery systems. Today, when a person swallows a pill, we expect the drug to be delivered immediately. But using this technology, we can design smart pills that deliver doses over extended periods of time. This can be very helpful for patients with Alzheimer's who tend to forget to take their own medicines. Another major application is continuous sensing of biomarkers and tumors inside the body. You can imagine a network of miniature sensors inside your body, sensing conditions and sending information to the outside world. For example, they can continuously monitor a person's gut microbiome or stomach condition. In the future, such information can be used for predicting diseases and enabling early intervention, because you can monitor the body from the inside. For example, you wouldn't have to get tested for coronavirus. You have a device that sits inside your body and automatically detects if you've contracted the virus and alerts you right away. And there are many other applications for wireless and batteryless microimplants, including long-lasting artificial pancreas for diabetes patients, and deep brain stimulators for treating patients with epilepsy and Parkinson's. So we could enable all these applications with wireless microimplants in deep tissues. The problem, however, is that existing batteryless microimplants can only work at very shallow depth, or cannot really adapt for different in-body conditions. In this talk, I present Micromedic, a wireless, batteryless, and self-reconfigurable microimplant. Micromedic is the first system that enables cross-tissue wireless and batteryless connectivity. It's also the first batteryless microimplanted system capable of self-reconfiguration for energy harvesting and backscatter communication inside tissues. I'll tell you how we've designed, fabricated, and evaluated our microimplant in different tissues, including both in vitro and ex vivo environments. And I'll show you how our fully integrated system, which includes both the IC and the antenna, consumes 350 nanowatts and supports up to 6 megabits per second. But before I tell you how we built Micromedic, let me tell you why bringing batteryless connectivity deep inside the human body and across tissues is very difficult. Remember that we have a wireless batteryless implant, and we power it up using a wireless signal from the outside. And let us say I designed the microimplant so well that it can power up and operate inside the stomach. Indeed, a few years ago, we demonstrated the potential to power up microimplants deep inside the body. But if I take the same microimplant and put it somewhere else inside the human body, for example the large intestine, it does not power up, even if it's the same depth inside the body. You might be wondering why. The reason is that for the node to power up, it needs to be able to harvest a certain minimum amount of energy. But here's the thing, even if it receives the same amount of power, it does not power up. And the reason is that the surrounding tissue will impact the microimplant properties, including the antenna efficiency and gain, and prevent it from harvesting enough energy to power up. The main problem is that antenna resonance is impacted by surrounding tissues. Let me explain to you what I mean by this. If we take the microimplant and put it in some tissue, for simplicity, let me consider a simple muscle-based tissue like the stomach. If we transmit a signal around 900 MHz in the ISM band, then the node harvests a certain amount of energy. Let's say the turn-on threshold is here. Then the harvested energy at 900 MHz will be higher than the threshold, and the sensor powers up. Now let me take the same implant and put it in another tissue, which is primarily fat. Now, if I transmit the same signal as before, the harvested energy will be much lower, and as a result, the sensor does not power. To understand what's happening, I repeat the same experiment in muscle, but I change the transmit frequency, and I plot the harvested energy as a function of frequency. This is the plot that I get, and as you can see, because this antenna was optimized for muscle, the peak is around 900 MHz. However, if you put the same implant in the fat tissue and do the same experiment, the peak shifts to around 1100 MHz, which is why it can power up inside the ISM band. So why does this happen? The reason this happens is that to maximize efficiency, in-body antennas are typically designed to be resonant with the harvesting chip. Resonance is the natural frequency at which something vibrates. For example, if I plug this glass cup, I hear a specific tone that corresponds to its resonance or natural frequency. Similarly, antennas have a natural frequency that's impacted by the surrounding environment, and when they are excited at this frequency, they're very efficient. This is why the resonance shifts when you take a resonant antenna in muscle and put it in fat. So how can I overcome this challenge and power up the antenna inside the fat tissue? Well, one option is that I can transmit at 1100 MHz, but this wouldn't be compliant with regulations because it's outside the ISM band. Another option is that I can crank up the transmit power at 900 MHz to overcome the threshold energy in fat, but this wouldn't be safe for human exposure. If you want to make the antenna resonant in fat at 900 MHz, we need to change its dimensions and make it bigger. Doing so would allow us to shift its resonance back to the 900 MHz. But we can't change the dimensions of the antenna after we implant it or ingest it inside the body. Moreover, as the microimplant moves inside the body, it will experience different tissues and might lose connectivity altogether and be unable to power up. Ideally, what I want to do is design an implant which can reprogram its resonance so that it can adapt to the surrounding tissues. The natural question becomes, how can we reprogram the resonance of an in-body microimplant? In general, in-body antennas are designed as rigid loop antennas, resonating directly with the harvesting chip. And if you plot the energy harvesting voltage versus frequency, we get a single peak as we can see in the plot on the right, similar to the one we've showed earlier. And this resonance is fixed. To overcome this, our idea is to introduce a coupled structure in order to control resonance. Let me tell you what I mean by this. I'll add another loop to my antenna. Now, for those of you who are familiar with antenna design, you know that this is usually not a good idea. Having two antennas close to each other typically results in an undesirable phenomena called coupling. Basically, because the two antennas are close to each other, their electromagnetic fields interfere with each other. For example, it changes the harvesting properties, as you can see in the plot here. While it is true that coupling is usually undesirable, I want to use this phenomena in order to shift the resonance frequency and build a programmable antenna. And the way I'm doing this is by adding a tuning capacitor that allows me to control the intensity of coupling. By controlling the coupling, I will be able to shift the entire curve or resonance down in frequency, or for example, to the 900 MHz ISM band. So this coupled structure with on-chip tuning allows me to build a programmable antenna and shift its resonance frequency to different in-body environments and enable cross-tissue operation. Next, let me show you why this approach allows us to change the effective area of the antenna. To do this, let's go back to the implant in muscle tissue and simulate the current flow in the antenna. Here, the chip is tuned to a certain capacitance C1, and the heat map shows the current flowing in the antenna. The simulation shows that the entire antenna experiences a time-varying current distribution. This shows that the entire antenna is resonating at that frequency. However, if we put the same implant in a primarily fat tissue, we see a very different current distribution. Here, the current in the outer loop is almost zero, which means that the entire antenna is not resonating and not efficient. Now, let us see what happens when we tune the on-chip capacitor to control the coupling. Notice that now the current distribution changes and the entire antenna is resonant. This way, we have changed the effective area of the antenna and have made it more efficient. This allows us to boost the harvesting efficiency and power it up inside tissue. So the key take-home message here is that Micromedic's antenna design allows reprogramming the resonance and cross-tissue energy harvesting. Now, you might be wondering, why did we choose this design rather than simply using a single loop and trying to program its resonance? In practice, a single loop would give us very little leverage and wouldn't provide the desirable programmability properties. For example, there's a few other complexities that I didn't want to go into here, such as gain and impedance, and this coupled design was the result of many design iterations. In this discussion, I've also only described antenna programmability. In practice, we also need to program the impedance matching in order to ensure resonance. And in our paper, we describe how Micromedic design extends beyond antenna programmability and also programs the circuit impedance matching. Great, so now we have a way to enable microimplants to power up irrespective of the tissue. But remember, we don't want to just power up the implant, we also want to communicate and send information from inside the body. And the natural question that arises is, how much throughput can Micromedic sustain? And the challenge here is that there is a trade-off between throughput and availability. Let me tell you what I mean by this. Let's take a microimplant inside tissue and zoom in on it. For simplicity, I'll consider a very simplified model consisting of the antenna, a backscatter switch, and an energy storage capacitor. Specifically, remember that our microimplant powers up by harvesting energy from wireless signals and stores this energy in a capacitor. And it communicates at ultra-low power via backscatter. And what I want to do is plot the stored voltage, or energy, in the capacitor as a function of time. When the wireless device outside the body sends a wireless signal, the microimplant harvests energy, and the voltage stored rises. But when the device starts backscattering, the voltage decreases over time. Moreover, if it communicates or backscatter at an even higher rate, then the voltage will decrease even faster and the microimplant will die. This shows that there's an inherent trade-off between throughput and availability. So how do we deal with this problem? One option is to be conservative and always transmit at a lower rate. However, if I were to do that, I wouldn't be able to achieve high throughputs, which are important for demanding tasks, like sending images from inside the body. On the other hand, if I were too aggressive and always transmit at a higher rate, then I would suffer in terms of node availability. The node would die off, and you might miss important biomarkers from inside the body. Ideally, we'd like to be able to transmit information at the best possible rate and adapt to the available power. To do this, Micromedic performs bitrate adaptation by tracking circuit-level sensor hints. Let me tell you what I mean by this. Instead of choosing a fixed rate, we vary the rate of the oscillator, and the way we do this is by tracking the voltage at the capacitor. Specifically, we have a 3-bit ADC that samples the voltage and maps it to a specific rate. For example, if the voltage increases, the mapper can choose a higher rate to increase throughput. And if it decreases, it can choose a lower rate in order to maintain availability. Micromedic rate adaptation enables scaling the throughput up to 10 megabit per second and power consumption down to 350 nanowatts. Additionally, in the paper we describe how to extend this to matching and antenna resonance adaptation in the energy harvesting mode, and how the receiver can automatically adapt to these changes. Next, let me tell you how we implemented our system. We implemented Micromedic design as a fully integrated chip fabricated using 65 nanometer low power process. The chip is around 1 millimeter squared. We also designed and fabricated our coupled antenna design as printed microstrip on a flexible PCB substrate. Here's one of our sensors in my hand. As you can see, I can roll it in pill form or potentially laminate it on an organ. And here's a magnified micrograph of the die. The chip has different blocks, including those for programmable antenna tuning, tunable matching circuits, the logic for reconfiguring, energy harvesting circuits designed as a 6-stage rectifier, and the power management unit, which regulates the voltage for the rest of the chip. Finally, we have the receiver chain, which decodes the input bits, and the backscatter switches, which enable transmitting data back to the reader. The chip also incorporates a lightweight MAC layer and protocol, and the overall power consumption can scale down to as little as 350 nanowatts. We also implemented a reader to power up and communicate with the node from outside the body. The reader was implemented on USRP N210 software radios with SBX daughter boards. We've evaluated our system in different environments. First, we demonstrated the operation in an in vitro setup. As most tissues are either oil-based or water-based tissues, we tested our system in the two extreme cases of oil-based setup and a saline solution setup. We've also evaluated the performance of our system in an ex vivo setup, where we've tested the operation under different meat tissues, such as a lean tissue, fatty tissue, or a mixed one with bones. Now let me show you some of our results. First, let me show you how we can power up the microimplant across different tissues. In this experiment, an external reader transmits a continuous signal at a fixed power and distance, and the microimplant is placed in different tissues. First, let me show you the results for the fixed, non-reconfigurable design. Here we plot the harvested voltage versus frequency. Remember that we need the harvested voltage to be above a minimum threshold in order to power up. We're also only interested in the performance in the 900 MHz ISM band. And here are our results. This design was optimized to power up in oil-based tissue. So you can see that, indeed, its voltage in the oil-based tissues is above the threshold voltage. However, for all other tissues, the harvested voltage is below the threshold. This result again demonstrates that it's not possible to power up the implant across tissues without reconfigurability. Next, let me show you the results for Micromedic's self-reconfigurable design. As you can see, this design can achieve a voltage at or higher than the threshold across all different tissues inside the ISM band. This is because by reprogramming its resonance, Micromedic can adapt to different tissue environments. By tuning both the matching and antenna resonance, we obtain the optimum values for achieving the highest energy harvesting efficiency. For example, by adding a 1 picofarad of matching capacitor and reprogramming the antenna with a 1 picofarad of tuning capacitor, we can power up the node in meat, which wasn't possible in a single rigid structure. These results show that Micromedic's reconfigurable design for changing the resonance allows it to power up across all tissues. While I focus on the ISM band here, in the paper we also extend on this and show that we can tune for other frequency bands, such as the radio band in China. Such programmability brings other benefits such as allowing cross-tissue operation across countries, or for example, when someone is traveling across the world. Next, we ran a series of experimental trials to assess the importance of rate adaptation. We experimented with different rates, distances, transmit power, and packet sizes. I want to share with you one of our results regarding availability, which is the percentage of time the node is on to the total time where the external reader is sending a downlink signal. Here, I plot the node availability for different backscatter rates. We ran around 30 experimental trials, in total covering low power, high power, and varying power environmental setups. The dashed line here corresponds to 90% availability. And here are our results. As you can see, in the high power settings, the node availability is more than 99% for the low rate mode, and similar in the high rate mode. However, the high rate mode provides an effective throughput as high as 11.5 megabit per second compared to less than 0.5 megabit per second in the low rate mode. This shows that when the power is high, having higher rate is more desirable, as it provides both high availability and throughput. Next, let us see what happens when the available power is low. Here, the low rate mode still has an availability of almost 94%, while the high rate mode drops to around 80%. This might sound like a good number, but this means that for 20% of the time, the node is not available to communicate with the outside world, which may not be suitable for critical applications. This shows that if we care about availability, then we might want to be conservative and choose the lower rate mode. More importantly, this result shows the importance of rate adaptation in allowing us to adapt to varying channel conditions. We also implemented a simple rate adaptation protocol, and here are our results. As you can see, even at low power, the adaptive rate maintains an availability higher than 90%, while providing higher overall throughput than the low rate. These results show the importance of Micromedic's bitrate adaptation in trying to achieve best effort throughput while maintaining high availability. While we have experimented with one specific rate adaptation protocol, Micromedic's design itself is general and can be used to implement different rate adaptation schemes depending on the higher level applications. To conclude, in this video, I presented to you Micromedic, the first fully integrated, self-reconfigurable wireless and batteryless microimplant. Our microimplant enables cross-tissue connectivity by introducing reprogrammable structures for resonance and rate adaptation. I also described to you how we fabricated our microimplant and evaluated it in ex vivo and in vitro tissues. I want to wrap up my talk by saying that this research is very exciting for me, because on one hand, it bridges ideas from various disciplines, and on the other hand, it paves way for a new generation of medical devices that can be used for disease diagnosis and treatment. Thank you very much for listening.